In this video, we're going to discuss the multiplicity of states, that is the number of microstates for a particle inside of a box at some temperature. And so we want to eventually do a three-dimensional normal box, but we're going to start out by talking about just a two-dimensional box because it's a little bit simpler. Okay, so for a two-dimensional box, we begin with the wave function. So the wave function of a particle in a two-dimensional box looks like this, where we have a sine function involving nx. Nx is our principal quantum number, our energy level in the x direction, and ny, which is the principal quantum number or the energy level in the y direction. This comes from exactly the same math that we did in the video where I introduced the particle in a one-dimensional box and solved Schrodinger's equation. All we've done is just added an extra dimension to it. In this case, our energy goes like this expression here, where we have an nx squared plus ny squared giving us our total energy. What we're interested in finding is how many states are there with this particular energy. So, as an example, I'm going to pick nx equals 7 and ny equals 0, which gives me an energy of h squared over 2ml squared times 7 squared. Now, the first thing I should say is 7 is way too small of a number for what we're interested in. We're interested in 10 to the 8th or something like that for our n. But it's going to be helpful to consider a small number just as we make the initial arguments about this. So we are at an insanely small energy level where none of the things that we would talk about here or none of the assumptions that we're going to make are terribly good, but the numbers are small enough that we can think about them well. Okay, so what I'm now going to do is I'm actually going to plot these energy levels in this kind of n space. So what this is each dot represents a possible state of the particle. So we only have one particle, and that particle has two variables that control its energy. Its nx level and its ny level. And what I've done is I've put a dot at each kind of, so this would be nx equals 1, nx equals 2, nx equals 3, etc. And the same for y. And so any given state, like this state here, would be nx equals 1, ny equals 2. It's just a way of being able to visually show how many states there are and what those states kind of look like in this n space. Okay, so the state that I chose, which is nx equals 7 and ny equals 0, falls right here. It's at 7 dots over to the right, 0 dots up because ny equals 0. Now, I know there's at least one other state with exactly the same energy, which is if ny equals 7 and nx equals 0, right? Because then, again, nx squared plus ny squared equals 7 squared. I'm here, right? That is the exact same energy level. Now, what I would like to argue is that every point that lies along this dotted line here also has exactly the same energy. Okay, so what we can do is we can rearrange this equation here to solve for nx plus ny, or nx squared plus ny squared. In this case, everything on the right side of my equation, 8ml squared u over h squared, all of those things are constant because we've chosen energy to be a constant. L is the side of my box, the length of the side of my box, so that's not changing. M is the mass of my particle, that's not changing. So everything on the right side of this equation is a constant. And so if I have an equation that looks like x squared plus y squared equals constant, that is the equation of a circle. So I can actually draw that circle, or the quarter of the circle that lies in the first quadrant, here. And any point that lies along this quarter circle must have the same value of nx squared plus ny squared, and therefore must have the same energy because the energy is just constants multiplied by nx squared plus ny squared. Now, this is the part where the explanation doesn't make a ton of sense if I choose 7. because there's no points that actually fall directly along that line for n equals 7, or nx squared plus ny squared equals 7. That being said, let me make an argument to you about why it would make sense that the length of this line should tell you about how many points lie along that line. Okay, so here is how the argument goes. Imagine that you are walking along a path, and I tell you that every 1 meter along that path, there's a stone. And I say, okay, if you walk 5 meters down that path, how many stones will you pass? And you would say, okay, well, there's a stone every 1 meter, and I walked 5 meters, so I passed 5 stones, right? And so the idea would be that the number of stones is equal to the number of meters that you traveled, right? So we're relating a discrete quantity, how many stones did you pass, to a non-discrete quantity, right? A continuous variable of number of meters. But as long as the distribution of your discrete quantity is constant, as long as there's a stone every 1 meter, then this will hold, right? And we can make the same argument here where we think about each of these dots as kind of a stone, right? And we say, okay, well, if we walk this distance, even if it's in a curved path, this is about how many stones we will have passed. Now, here is yet another wrinkle. If I don't walk exactly straight to the right, say I walk up at an angle like I've drawn this r vector here, well, I don't really pass a stone every 1 meter, right? I might pass a stone every 3 meters or every 5 meters, which would be a problem if we were going to deal with numbers on the order of 3 or 5. But in the end, we are going to get such enormous numbers, right? 10 to the 50 or something like that, that it doesn't matter if we're off by a factor of 3, right? It's going to matter if we were off by a factor of 10 to the 50, that would be a problem. But being off by a factor of 3 on a number that is 10 to the 50 big is not really going to change our final answer, right? So we are looking for good simplifying estimates, and this fits, right? If I tell you the length that you traveled, you can tell me how many energy states you passed. So what we're going to do is we're going to try to figure out the length of this line here in n space, right? And that's going to tell me how many dots I went through, and each dot is a microstate. So if I know the length of the line, I know how many microstates fall along that line, right? And in the end, what we're going to do is we're going to choose an n that is enormous, 10 to the 8th, 10 to the 10th, something like that. And it's going to be that the dots are so close together that the idea that it really matters kind of what angle we choose won't be that big of a deal, right? So my argument here is that, yes, this is not a perfect assumption that we are making, but it's a pretty good assumption, and it allows us to actually do the math. Because for something like 10 to the 8th states, I don't want to go around trying to count every single state that has exactly the same energy. I want a simplifying mathematical statement that allows me to estimate it. And that's what we're going for here.
Now what we want to do is apply our information from the 2-dimensional model to a 3-dimensional model, because of course all real gases live in 3 dimensions. So extending our energy equation to include 3 dimensions, we get the equation at the top, which indicates that u is a function of nx squared plus ny squared plus nz squared, with the same constants out front, h bar squared over 8ml squared, where again, h is Planck's constant, m is the mass of the particle, and L is the length of one side of the 3-dimensional box. So this equation here gives us a sphere, a spherical shell in n space, right? Nx squared plus ny squared plus nz squared equals a constant is the equation for a spherical shell of radius r sub n, where r sub n is given by the equation in the center of the screen. And instead of using the length of a line in 2 dimensions, we now use the surface area of this spherical shell in 3 dimensions to indicate the number of microstates at a given energy. So our R here is the radius of our spherical shell, and the surface area of that spherical shell gives us the number of potential microstates that all have the same energy U. And because we want nx, ny, and nz to all be positive values, we are not allowed to have negative n's. We only want the surface area of that spherical shell in the first quadrant where all of those values are positive. So in this case, for a single particle, we would need 1/8 of the actual surface area of that spherical shell in order to find our multiplicity.
Now, imagine instead of one particle, we have big N number of particles, some macroscopic number of particles. So when we have N, big N number of particles, then our energy looks like the sum of the energy of each particle individually. So each particle contributes this amount of energy, where each particle has its own unique nx, ny, and nz values. So what we need to do is say that our energy is our coefficient up front, because that's the same for every particle, and that gets multiplied by a sum over all of the particles from 1 to big N of our energy state values for each particle, right? So we have nx1 squared plus nx2 squared plus nx1 squared plus ny1 squared plus nz1 squared plus nx2 squared plus etc. So we keep adding up all of these values, and this creates, instead of creating the surface of a sphere like we did with the 3-dimensional example, it's going to create a hypersphere, which is a higher dimensional version of a sphere, which still obeys the equation, basically, that if you add up, so this is the equation that we're looking at here, if you add up all of the n's and all of these squared, you equal some constant, right? If I keep the number of n's to 2, I get a circle in 2 dimensions. If I keep the number of n's to 3, I get a sphere. If I keep adding them, I get what's called a hypersphere, which is not something that we can draw in 3 dimensions or represent well in 3 dimensions, but it is a mathematical construct that we can see has the same basic features as a sphere. That is, we add up the square of the kind of position, right, the n space position in all of these dimensions, and we get a constant, this radius. And of course, this radius is just equal to this value of related to the energy, just like we found in 2 dimensions, right? It's just that now this U is going to be much, much bigger, because instead of having 1 particle, we're going to have 10 to the 23 particles that we're adding up, right? So we're going to have this much bigger radius, but it's going to be in a much bigger space. Okay, so if we could hypothetically find the surface area of this hypersphere in this super high dimensional space, depending on how many particles we have, we could hypothetically then find the number of microstates that lie along this surface area. Okay, so what we need is we need a area formula for some super high dimensional space, right? And in general, the surface area of a hypersphere, right, a sphere-like thing that exists in higher dimensions than 3, is given by this formula here, which is derived in the back of the book, where little r here represents the radius of that sphere, and little d is how many dimensions the sphere has. Okay, so what we want is we want to set the number of dimensions equal to 3 times the number of particles. And this is because each particle contributes 3 dimensions to our radius, right? So we have 3 dimensions for the first particle, we have another 3 dimensions for the second particle, etc. So the dimensionality of our hypersphere is going to be 3 times n, the number of particles that we have. So this might be 3 times 10 to the 23 dimensions in our hypersphere. Of course, we can't draw anything in that many dimensions, but we can at least use it as a mathematical formulation. Okay, so now taking this area formula and plugging in d equals 3 times n, we come to this. Oh, and r, we plug in little r, we plug in our radius of our hypersphere here, and we come out with this equation. And we're going to make a few adjustments to this equation, and then we're going to make one correction to it as well. Okay, so the big things are that n is much, much bigger than 1, such that 3n minus 1 is the same thing as 3n. And 3n over 2 minus 1 is the same thing as 3n over 2. So we're just going to throw out those factors of minus 1 because they don't really change our total answer by a big enough margin to bother to keep track of them. Okay, the other thing is that L cubed looks like the volume of our box, right? We're looking at a box that is L by L by L, right? Each side has a dimension of L, so L cubed is V. And what you'll notice is this, from the L squared, the over 2 in the formula cancels out the L squared, so we get L to the 3n, which looks like volume raised to the n. So this is our temporary formula, and we need to do one more correction to it before we are at the final formula for the multiplicity of states for an ideal gas. Now that we have an equation for the area of our 3n dimensional hypersphere, we need to convert this into a formula for the multiplicity, the number of microstates in our system. And we're almost there. The problem is that our area formula takes into account the area of the full sphere, whereas we only want the area of the sphere that corresponds to positive values of our energies, our nx, ny, nz. So the analogy to this is that when we thought about just 2 dimensions, we only thought about the area, or the length of our circle in this case, that was in the positive quadrant here, because we require that our nx values and our ny values be positive, right? These are energy quantum numbers, and they are only positive. So what we need to do is we need to figure out how to do the same thing as taking the positive quadrant of a circle, but in 3 to the large n, the number of particles, dimensions, right? So the way to think about this is, let's imagine that we are trying to figure out how many quadrants there are total for some dimensional sphere. Let's begin by considering the number of quadrants in just 2 dimensions. So if I look at my axis here, from the axis I can move in the positive x direction or the negative x direction. So I have 2 options for how the directions that I can move in n1. In n1x, in the x direction here. For y, I also have 2 options, right? I can move in the positive direction or the negative direction. And if I multiply my number of options in each case together, I get 4, right? 2 times 2 is 4 options, which means there are 4 possible quadrants, right? I can have positive x and positive y, positive x and negative y, negative x and positive y, or negative x and negative y. That's 4 possible options, 4 possible quadrants. Now if we move to 3 dimensions, well, now we have another set of options where we can do to move to the positive z or the negative z direction. So each of these quadrants, right, I have 4 options here. And then on top of that, I get to choose another 2 options, right? So for all 4 of the options that I outlined here, I can choose positive z, which gives me 4 options. Or for all 4 options here, I can choose negative z, which gives me another 4 options, for a total of 2 times 2 times 2 is 8 quadrants. And if you think about a sphere in 3 dimensions, and you think about the amount of that sphere that lies in the positive x, positive y, and positive z quadrant, it's 1/8. 1 over 2 times 2 times 2. Okay, so it looks like in 3 dimensions, we have 2 to the 3rd number of quadrants. We can extend this by adding on another 3 dimensions. So now I have 2 options for each of my particle 1 dimensions, right? Positive or negative for each of those. And then I have another 2 options for each of my particle 2 dimensions that they can each be positive or negative. Using the same logic, I would have 2 to the 6th, right, number of possible quadrants. I have 2 to the 6th quadrants for a 6-dimensional hypersphere. Okay, and we can extend this all the way into 3 to the big N dimensions. I have 2 to the 3n dimensions, then I have 2 raised to the 3n possible quadrants. And I only want one of those quadrants, because only one of those quadrants corresponds to choosing the positive value for every single n, right? There's only one in 2 raised to the 3n possible quadrants in which all of the n's are positive. So what we need to do is we need to take our area formula, which is the area of the hypersphere over all of the quadrants, and we need to reduce it down to only one of those quadrants. So what we do is we say that our multiplicity is equal to this area function divided by 2 raised to the 3n, because this is the total number of quadrants, and we only want one of them. So we need to divide out all of the other quadrants. Okay, so in doing so, what you'll notice is that this 2 to the 3n, or 1 over 2 to the 3n, which comes from counting up our quadrants and dividing out the ones we don't need, cancels directly the 2 to the 3n in our area equation, leading to this formula. And we've made one other simplification, which is we have dropped this 2 out front, because the idea is all of these numbers are raised to the 3n. So for example, pi raised to the 3n over 2, that's pi raised to the, say, 10 to the 23rd, which is an enormously large number, and multiplying that number by 2 is not really changing anything. So just for simplicity, we drop the 2 out front. And this is, as a general rule, for these enormous numbers, if you have something that's not raised to a really big power, it's probably okay to drop it if you're trying to make an estimate, right? So anything that's not getting raised to the power of n here, or something close to it, is probably a small correction that we can drop for our estimates like this. Okay, now we need to make one more correction. And that correction is for the fact that the particles in our ideal gas are indistinguishable. So now we found the multiplicity function omega for distinguishable particles. Assuming that we can individually label each particle and separate between them, this is the multiplicity. So now all we need to do is take into account the fact that we can't actually tell the difference between individual particles within an ideal gas. And that means that we need to divide our multiplicity by the number of ways of rearranging all of the particles, all of these identical particles. And for n particles, there are n factorial ways of rearranging them. So we divide by n factorial, and our multiplicity function becomes this. So this is the final multiplicity function for an indistinguishable ideal gas.